Okay. So I'm going to be talking about drought over North America under different forcings, and I'm going to be using the last Millennium Ensemble from CESM. So typically when I'm doing a talk like this, I'm often comparing the paleoclimate record to model simulations, and oftentimes I'm looking at the models to try to see if we think they're going to do a reasonable job of simulating decadal and even longer time scale variability. So using the paleoclimate record to potentially constrain the models in that regard. And that's usually with an eye towards projecting future hydroclimate. But another way to look at this is actually to flip it on its head. So we know there's been decadal and longer time scale variability in the climate system. We see that within the paleoclimate record, but we know very little about what the origins of that variability is. So we can actually use the models to better understand the real world. Specifically, I'm going to be looking at the dynamics of the atmosphere and the ocean that lead to decadal and longer time scale hydroclimate variability. And what I'm really going to be asking is, are decadal and longer time scale droughts forced? Okay? And by forced, I mean two things. I'm going to look at the external forcing of droughts. So this is going to be changes to solar variability, volcanic, greenhouse gases, land use, and other external forcings that then might drive drought. I'm also going to be looking at changes to the SST boundary conditions. So these are typically internal modes of atmosphere-ocean variability, things like ENSO or the AMO or the PDO that then drive droughts. And then, of course, the external forcing can actually project onto these internal modes of variability to potentially change their characteristics and, again, give us droughts on these timescales. And I'm going to be particularly interested in this point here. So this isn't really new. So a case study would be looking at mega droughts over southwest North America. So when we look at drought on this time scale over the extratropics, typically we're going to use the tree ring record. This is the grid corresponding to the North American Drought Atlas. We call this the NADA for short. It's a tree ring-based reconstruction of June, July, August average Palmer Drought Severity Index. So PDSI is a metric of near-surface soil moisture. It's really commonly used in drought studies. It's what we're going to use throughout this talk. So typically in these studies, what we do is define a box. And you can see a box here corresponding to the southwest. And then we'd average hydroclimate over that box to produce a time series. So this would be the box average of PDSI. We're looking over the last millennium. And when we look in this time series, we see multiple decadal and perhaps even longer time scale droughts. And we call these very persistent and severe droughts, mega droughts. But we know very little about how they occurred and what were the atmosphere and ocean dynamics that drove these features. So one way to approach this is to look in models and try to understand how models simulate these things. And I highlight a couple papers here that have done this. An obvious first question, of course, is do models simulate megadroughts? We're not going to ask how these things happen in models if they don't even have them in the first place. And the answer is yes. We see these features in pretty much all model simulations. Are they forced? So do the external forcings in these forced transient simulations, for instance, at the last millennium, drive these models, drive these megadroughts? And the answer appears to be no. It really appears to be a response to internal atmosphere-ocean variability. And in fact, if you look a little bit closer, what we notice is that oftentimes we get these very persistent and severe droughts, even widespread over space, that are purely the result of stochastic atmospheric variability. So there doesn't even appear to be a dominant role for the SST boundary conditions in driving these features. I want to point to a paper that's probably coming out soonish from Sam that explores some of this, and it'll be in Journal of Climate. So can we expand on this? And I think there really is one way that we can, and that's that drought is a spatiotemporal phenomenon. But in those studies and in that little introduction I gave, we were looking at a time series. Okay, so we were really only looking at the temporal characteristics of these droughts. Instead, what we'd like to do is identify and characterize droughts in 3 dimensions. Those dimensions being latitude, longitude, and time. So this is that same time series. I'm going to choose an example drought here by eye, highlighted in orange. What I'm showing here is a 3-dimensional grid. So we've got latitude on the vertical axis, longitude on the first horizontal axis, time on the last horizontal axis. The latitudinal and longitudinal extent of that southwest box are those arrows, and the temporal extent of the drought is the final arrow. Each of the dots there are space-time grid points. And so what we'd like to do is assign to each of these space-time grid points whether we're in a drought or a normal state. In this sort of arbitrary binary context, a drought state could be assigned a value of 1, a normal state a value of 0. Okay? So that sounds relatively straightforward, something that we could do. But there's something that we know about drought, and that's that drought tends to have some spatiotemporal consistency. And so ideally, we'd like these 1s and 0s to be sort of organized in space-time. And it just so happens that that is a problem that's well posed by finding the most likely configuration of a binary Markov random field. So the idea here is within the context of the drought, this algorithm, which is a map estimation, is going to identify clouds of ones, so clouds of drought that are contiguous and distinct from all other clouds of drought. And it turns out that solving this problem isn't actually possible, but you can estimate it using machine learning methods. So we're going to construct an algorithm using machine learning methods to solve this problem and identify these droughts. So this would be the output over this domain here. What we see is a drought that is kind of centered over that box and during this time period, but clearly extends well beyond that. It's clearly a distinct feature that we're looking at here. So we're getting some more information. So we can ask a lot of things about this drought. We can ask about its shape, about its propagation through space-time, its width, its length. Unfortunately, I don't have time to do any of that. So what we're really going to just talk about is the severity of this feature. So you can imagine just unwrapping these grid points here into a two-dimensional view. I've colored each of the grid points by their PDSI value. Orange is negative, so those are drier conditions. I'm going to define a metric of severity, which is just integrating or summing the PDSI over all of these space-time grid points in a drought. So for this particular drought, it would be about negative 870. So that would be the integrated severity metric that we're going to be using here. So we're going to apply this algorithm to the last Millennium Ensemble, as the title indicated. We're going to be looking at 30 total runs. 12 of these are fully forced, so they have transient external forcings, and we're looking at all of them. And then a number of these have only a single external forcing factor. So for instance, we have 5 simulations that just have volcanic. All the other external forcings are fixed. In each of these runs, we're going to calculate PDSI. We're then going to throw this algorithm at it over North America. So we're going to look at the full of North America for the last 1,000, well, not the last 1,000 years, but from 850 to 1849, so before the rise of anthropogenic greenhouse gases. And we're going to identify the 50 most severe droughts using that metric in each of these simulations. So in total, we're going to be looking at 1,500 different droughts across all of these runs. So I'd really like to talk about the SST boundary conditions and how they drive these droughts, but I don't have time to do that. I do want to make a quick plug. I'm sure I want to make this plug because I think this sort of coupled methodology using machine learning methods is something that might be useful within the context of the LMR. In particular, in searching through that uncertainty space, I think is probably a big data problem. And so this is kind of hands-off, but still can constrain these runs and give you some information. So we got 1,500 droughts. They're not just in the Southwest. They're located all over North America. So how would we even begin to constrain the dynamics underlying these droughts? In self-organizing maps is a technique that probably a lot of people here are familiar with, but it actually works quite nicely for this purpose. So ostensibly what we can do is we can take the geopotential height anomaly for each of these 1,500 droughts. We can throw that pattern into a self-organizing map algorithm. And what it's going to do is it's going to cluster the maps that are similar together. So we're going to identify sort of the atmosphere-ocean dynamics that are similar across different droughts across these different runs. And I'm not going to go into any detail here, but we can ask what are the SST boundary conditions associated with these different SOM modes that we identify. We can ask where the droughts occur when we get these different SOM modes. Do they shift north? Do they shift south, southwest? Okay. So I think it really might be a useful approach if you've got a big data problem like an LME. So this is the good stuff. What I really want to talk about is the external forcing of drought. Typically, when we approach this problem, we're going to take runs with transient external forcings, and we're going to compare them to a control run that's got constant pre-industrial forcing conditions. So what I'm showing here is the average characteristics of the top 50 most severe droughts. So I've identified 50 droughts, each of these simulations. I'm looking at their average severity. This is impossible to see, so I have to apologize. This is the mean of the 12 fully forced simulations. There's also a range here. The range goes from about there to there. So never use yellow in a PowerPoint. That's a lesson to be learned. For each of these, for all of the other individual forcing runs in the pre-industrial control, I'm looking just for each individual run, the average severity. Okay? So if there's some systematic difference, if some of these are systematically falling outside the range of what we're getting across those 12 fully forced simulations, it suggests that perhaps there's something dynamically happening there to give us some change in the severity of these very severe droughts. And what we do see is that this pre-industrial control, again, here's the bottom of that range, does fall below the range of those 12 fully forced simulations. Some of that might be sampling. Maybe if we had 40 fully forced simulations, they'd start to overlap each other. But this is intriguing, okay? As we go and look at the individual forcing factors here, what we see is we can't really pinpoint one individual forcing factor that appears to cause this discrepancy. It's not like volcanic is the one that does it. If we had greenhouse gas, it would all fall down here. They all seem to fall within the range of that fully forced run. So despite that, I think we still have something that we can try to get at here, is to try to better understand these differences. So the first thing we might ask is, well, maybe there's some direct forcing. Okay, so we'd have a period where there's high solar, maybe there's no volcanoes. So globally, it's warmer than average. So given precipitation deficit during a drought, perhaps it's just warmer overall, there's more evaporative demand, and this drought is more severe than it would have been otherwise. Okay? So is that happening? And the answer is no. There's really no evidence at all of this direct impact of forcing. Maybe these droughts are just happening in a different location. So maybe in the control run, we have more droughts in the southwest, but when we have volcanic forcing, we get more droughts over the northwest. That's also not happening. There's no evidence for that at all. The last thing is maybe the modes of internal atmosphere-ocean variability driving these droughts are different under different forcing conditions. Okay? And again, there's really no broad brush, at least, statistical evidence for that. So what's going on here? Why are there these differences here? And one possibility is that the external forcing is actually projecting onto the internal modes of variability to change their characteristics. I want to note that's really hard to get at. It can be very difficult to tease these things out. But we've got 30,000-year model simulations, so it might just be enough data to try to understand this process. Before we go further, I think it's interesting, or at least important, instructive, to split PDSI out into its components. So PDSI is driven by inputs from precipitation, outputs from evapotranspiration. Typically, we estimate that by calculating PET and then scaling that by a constant factor. So in the same sense that we summed the PDSI over all the grid points in a drought to get this severity index, we could sum the precipitation during that drought and the PET to get a precipitation and PET deficit during these drought features. So this is exactly what I've done here. We got PDSI, or the severity on this axis, precipitation here, and PET here. Each one of these dots is one of the 50 most severe droughts in the 12 fully forced simulations. So 50 times 12, we got 600 total points here. I'm going to flip this axis, and I'm actually going to fit a convex hole in three-dimensional space to these points. So you can think of that as sort of stretching an elastic surface over these points to fully enclose them within a volume. Okay, so it's a volume that fully encloses these points. We can split this out into the constituent parts, and I got a yellow problem here again, but this is precipitation and PDSI. This is PDSI and PET. This is the space spanned by those 600 droughts. It's quite narrow. You can't really see it. It's really narrow. That's because precipitation is really the dominant driver of PDSI. This one's a little bit more wide. So we can compare this to, sorry, got ahead of myself. We can compare this to the 50 most severe droughts within the control run. And then we can identify the droughts that are within that forced run but fall outside the range of the characteristics that we're getting in the control run. Okay? So there's 21 droughts of these 600 that have PET and precipitation anomalies that fall outside the range of what we get in the control run. We can split these into two different categories. One of these groups, which is these dots here, are super severe droughts. So these have huge precipitation deficits. They're very hot. They have huge PET deficits, and they're more severe than anything we get in the control run. There's also some compelling droughts here that are denoted by X's. So these are actually cold droughts. So they're still some of the top 50 most severe within that forced run. But they're very severe despite the fact that they have relatively moderate PET anomalies. You're only really going to get a moderate PET anomaly during a big drought like this if you have anomalously cool temperatures. So that's why I'm calling them cold droughts. So I really love to show you what's going on with these, but it would take way too much time. But I want to note that there is one consistency across these anomalous droughts. And that appears to be that the forcing is projecting onto the internal modes of atmosphere-ocean variability. So really specifically, it's volcanic. That seems to be the major player here. I want to note that it's not just a volcano happening right before the drought happens. This volcano can happen 50 years before the drought happens. And it tends to drive internal variability that goes outside the range of what we get within that control run. Okay, so this happens in both the Pacific and the Atlantic. In the Pacific, it appears to be extratropical interactions, by which when a volcano goes off, you can get up to 50 years or even longer, where you have really regular, so super periodic and very large magnitude decadal variability in the tropical Pacific. In the Atlantic, there's a sea ice extent, AMOC, AMO feedback that appears to be very consistent and very important to drive the AMO outside the range of what you get in the control run. So ideally, we'd see this, and it would be easy to see, and we could tease it out every time, but it appears to be highly state dependent. So the atmosphere and the ocean have to be in exactly the right state when these volcanoes go off in order for this to happen. Okay? And that very strong state dependence suggests to me that we should ask, well, how important was the forcing really? Okay, so maybe the atmosphere and the ocean were just in this perfect state, and if we had let them run without a volcano, well, the internal variability was going to go crazy anyways. We still would have gotten this super periodic large magnitude internal variability. And we might be able to test that within an idealized modeling framework. And I would love to be able to do that. Unfortunately, for people that have worked with the CESM model, you know that if you want to restart the model to rerun these periods to see what's going on, you have to have a restart file. And for the LME, the restart files were only saved every 100 years on the 50-year mark. And so we really need one of these droughts to interact with that 50-year period. And it just so happens that only one of them does. And I'm marking it with an X, which you probably can't see. It's one of these cold droughts. This is not the drought I would have chosen. Okay, there's 15 other droughts I would have chosen before this one, but at least we might be able to do this, might be able to understand it better. So it's a 10-year period, 1450 to 1459, where we get a drought outside the range of that control run. As you'd expect, because it's cold, so we had to have cold conditions. There's a volcano. That should actually say year 3. So there's a volcano in the year 1452. Okay? So we're going to ask 2 questions. We're going to ask how likely were the SST boundary conditions during this drought. Okay, so we want to know if the trajectory of the internal variability is something that we would have expected to have happened. And we're also going to ask if that internal variability, so those SST boundary conditions, actually tend to give us this drought, or if this drought was just kind of random. If it was, you know, maybe the SST boundary conditions dry things out, but on top of that, you needed a ton of stochastic atmospheric variability. Okay? So to answer the first question, we're going to run 10 coupled simulations. So this is fully coupled. We're going to start it in 1450. We're going to run through the end of the drought in 1459. We're going to perturb the atmosphere with round-off errors and see what the trajectory of that internal variability looks like. Because there's a volcano that goes off during this drought, we're going to run 5 of these without the volcano, just to see what the impact of the volcano was on those trajectories. So this is the output. We've got the Niño 3.4 index, PDO. These are the subtropical cells of the Pacific Ocean, AMO, AMOC, and sea ice extent. Ooh, sorry. There's a lot of information here, so I'm not going to talk about all of it. I just want to note the orange runs are the ones with a volcano, gray without a volcano. The original run is the thick black line. So there's 2 things I want to point out. The first, when a volcano goes off in this model, it tends to spin down the subtropical cells. You can see that right in 1452, that the orange lines and the black line all go negative. Okay, that's a common response to volcanic forcing within this model. Oftentimes, the Birkenes feedback will then kick in, and you'll get a fully fledged El Nino event in the following year. And in fact, in many of these volcanic runs, we get a big El Nino that actually persists for 2 years in some of these runs. In this original run, however, we get the drawdown of the subtropical cells, but we never get that El Nino. And what happens is a lot like 2015. The Birkenes effect just never kicked in, so we don't get a fully mature or fully fledged El Nino. It looks like it's going to get there, but it never does that. And in fact, its internal variability looks much more like the runs without the volcano. Okay, so its internal variability is essentially doing what it would have wanted to do if it didn't have a volcano, despite the fact that it did have a volcano. The other thing that we see is we have a highly anomalous multidecadal variability in the Atlantic Ocean. So another common response, volcano goes off, sea ice extent increases, and you tend to have a decrease in the AMO that's mediated by the AMOC. You see this in most of these runs. The sea ice extent increase is much larger in this run, however, and the AMO change is much larger as well. So the AMO goes much more negative than any of these other runs. So in both cases, we seem to have some sort of stochasticity here to the trajectories of these internal modes of variability. It's hard to reproduce what happened. The other thing that we're going to do is see how important those SST boundary conditions were. We're going to run 17 atmosphere-only simulations over this period, so it's going to have the same SST conditions for these 10 years, but we're going to perturb the atmosphere and see the role for stochastic atmospheric variability. 2 of these we're going to run without volcanic, just to see if the volcano matters for the atmospheric variability during these periods. So what I'm going to do again is just integrate over the grid points that correspond to that original drought, the PET, temperature, and precipitation anomaly. Downwards on these plots would be indicative of drier conditions overall. Okay? I want you to pay attention specifically to the precip plot. This is the range of those ones with a volcano. Oh, sorry. This is without a volcano. This is the actual drought. It was nearly twice as dry. The precipitation deficit in this one run was nearly twice as dry as 15 more simulations with exactly the same SST boundary conditions. The only difference is we perturbed the atmosphere the first time step. okay? So there's a huge role for stochastic atmospheric variability. Yeah, the SSTs want to dry things out, but there's no chance, barely, of getting all the way down to here. It's much drier than we would have expected. We also see the same thing in PET. So the volcano goes off, and in fact, in many of these runs, what we get are negative PET, or what would be wetting conditions. This run, way outside that range. Part of that's just land surface coupling. And land surface coupling could play a role in how dry it is here as well. So there's some feedbacks here, but the PET anomaly is way outside the range of what we get in these other runs. So some quick conclusions. Even under the influence of strong forcing like these big volcanoes, there's still a huge stochastic component to these very severe droughts. However, I didn't get to look at some of the more interesting droughts. This would not be the one that I would choose. There's some droughts that are super severe, have amazingly periodic decadal variability in the Pacific. I would love to play around with those. I just need to be more creative than I am because I can't figure out how to at this point. And then why should we even care? Okay, so I looked at 21 droughts out of 600, or probably more than that, right? This is 30,000 years of simulations. If this happens that infrequently, why does it matter, right? I think it matters because this is likely happening on a range of scales and magnitudes. Okay, so despite the fact that in order to tease it out, I had to look at the most severe of these features, it's likely that these types of mechanisms, these dynamics, are happening on all scales, all magnitudes, and are probably important. The other point is that the Atlantic response within this model is much more consistent than the Pacific. I think it makes a little bit more sense, sort of intuitively, but the Atlantic role for drought in this model is very weak. And that's a common thing within models. They tend not to represent the tropical Atlantic part of decadal or multi-decadal variability in the Atlantic. By virtue of that, they struggle to represent the teleconnections that they should. So in the real world, perhaps that there's a stronger role for the Atlantic, and this part's a little bit more deterministic. The last point that might be interesting here is that often this internal response can continue, particularly in the Pacific, on the order of 50 years later. You get this very periodic, very large magnitude decadal variability. And understanding that might lead to some predictability of the system on the types of timescales that we really don't have predictability for internal variability. That's it.
Check, check. All right. So on that first conclusion, it reminded me of the early slide where you showed the control response compared to these other forced simulations for various forcing. And you only had n equals 1 for the control, but yet this seems to suggest you had an outlier for that. So, okay. Do you plan to go back and run more control simulations for that?
It's expensive, so it would be above my pay grade, so to speak. Yeah, it would be great, right? I mean, there really is. I mean, it's crazy to say that we've got a sampling problem. We're looking at 1,000-year simulations, but we have way more force simulations than control runs, and it is a problem. And I think a lot of those 21 droughts are purely sampling. Some of them are really close to the space spanned by the control run. There's no way it's not a sampling issue. So it would be better to constrain the statistics, and maybe, yeah, I don't know. I would love to be able to do that, but it's a tough problem.